Step 5, I can determine the slope of a line and if a function is linear. Let's talk about slope in terms of rate of change. If we're talking about the rate of change, we're talking about comparing one quantity as it changes to another quantity. In other words, think about things in life that have rates. Like you've heard of lots of different rates before. You may have heard of miles per hour. That's a speeding rate, or the rate that your car might travel. You may have heard of reading at a specific rate, like you can read so many pages per minute, or maybe you can type so many words per minute when you're talking about how fast you can type. You may talk about rates in life when you're talking about how much you get paid per hour. Maybe you make $7.50 per hour. That's the rate that you get paid. Typically speaking, when we're talking about rate, we're talking about something with respect to time, hours, minutes, and so on. It's not always the case, but usually it is. So in this first example, we want to know the rate of change in the temperature for the solution. So again, we're thinking rate. We want to know about how the temperature changes per minute. And I know I'm using those because I get them right here from the top of my table. The temperature is changing in degrees Celsius per minute. So if we want the rate, and this is a constant rate, meaning it's changing at the same speed or the same rate, all we have to do is look at our table here and pick any 2 points. It really doesn't matter which two. I'm going to choose this one and this one. Really won't make a difference. So how does the temperature change? Well, it started at 118 at the end here, 0.4, and we're going to subtract the 139.4. How did the time change? Well, we were at 12 minutes here, but here we're at 2 minutes. We're just going to subtract them. When I use my calculator, I get negative 21 over 10, which simplifies to negative 2.1 degrees Celsius per minute. So that would be the rate of change for my solution. All right, let's take a look at the next example. Now we are looking at a graph of a line talking about a swimming pool being filled. And we want to know the rate that the pool is being filled. How many gallons per minute? That's our rate. Gallons per minute is this pool filling. So when we think about the gallons, we want to look at how the gallons are changing over how the minutes are changing. In other words, I'm going to look at my gallons. So at this point right here on the line on the graph, I have 252 gallons. And I know that gallons come second because if I look at my chart, the Y values are gallons, and this is my X and this is my Y. So I know it's 252 gallons. As opposed to this point, I only have 108 gallons. So if I want to think about how something's changed, I'm going to take the 252 and subtract the 108. When I had 252 gallons, I had 7 minutes of time that had passed. When I had 108 gallons, I had 3 minutes of time. So that's how my time has changed. It went from 3 minutes to 7 minutes. And when I simplify this, I get 144 over 4, which is 36 gallons per minute. That's the rate of change for my swimming pool, how fast the swimming pool is being filled. Now, when we have constant rates of change, you can pick any 2 points on the curve or any 2 points in the chart. In fact, in our first example here, I could have easily picked these 2 points. And when subtract 126.8, I would get negative, whoops, switch back to my pen, negative 8.4. And when I subtract 8 and 12, I'd have 4. And when I simplify that, I would still get negative 2.1. The same will be true here. But the lines that we look at in the information that we're using won't always be straight linear lines. Sometimes, like in this next example, when we're talking about digital music and ebook sales, the line curves. Do you see this little curve towards the end? It looks like it kind of bends or curves. When that happens, we're not talking about a constant rate of change. And when you think about it, in life, rates usually vary. It's very rare that something moves at a steady, constant speed all the time. Even when you're driving in your car, you might have a rate of 65 miles an hour, but that's not always the case. If you think about your route to school, it might start off 25 miles an hour in your neighborhood, and then you're at 35, and then you just get on the highway, and then you're 65. So the speed or the rates can change. And that's the case in this next example when we're talking about sales. The sales change from year to year. So it is asking us for the average rate of change from 2004 to 2009. That means they want to take the rate of change from 2004 to 5, and 5 to 6, and 6 to 7, and so on, and average them. So think about what we do when we average. We add them all up and divide by the number of items that we've added. Well, we could do that, but we would rather do it simpler. In other words, if I could just draw a line from here to here. Do you see how steep that line is that I just drew? That's the average rate of change. Right here, it's steeper, steeper, steeper. The blue part is steeper, the red part is steeper than the blue part, all the way up to about here, and then the blue part is steeper than the red part that's kind of flattening out. So all said and done, this would be the average. So all we have to do to find the average rate of change from 2004 to 2009 is use the values at 2009 and the value at 2004. So for digital music, we would say 3,100 millions of dollars minus 200 millions of dollars. And then we're going to go from 2009 to 2004 because that's the range that they've given us. And when we subtract those, we're going to get 2,900 over 5, which is 580 million per year. Let's do the same thing for ebooks. We would take 165.8 and we would subtract 9.6. And again, the range is the same from 2009 to 2004. That's the range of dates they've given us. When we simplify this, we end up with 31.24 millions of dollars per year. Sometimes we won't have a picture. We'll just be given information in a word problem like this. Don't panic. We still know that we want to go from 2007 to 2015. So that's going to be our range of dates. So since we want to find the rate of change for both schools, let's just do two separate problems. On the left, we'll have State College. And on the right, we'll have Central University. All right, looking at the change of applicants from 2017 to 2015. I'm going to think of it kind of like points, like we did on our graph earlier. In 2007, how many people applied to State College? Well, it's right here. In 2007, this many people applied to State College. And in 2015, this many applied to State College. So in 2007, we have 23,142 versus 2015 when we had 29,563. So now, if I want to talk about the change in applicants, I can say that we have 29,563 in 2015 versus 23,142 in 2007. Again, that was from 2015 to 2007. And when I subtract these, I get approximately 802.6 applicants a year. Since we're talking about people, it would make better sense to say approximately 803 applicants per year. Similarly, when we look at Central University, now I'm going back to my information and I'm going to look at Central University and find information in my word problem that pertains to Central University. Here's my Central University information. So in 2007, we had 34,689 applicants. And in 2015, we had 36,107 applicants. So again, talking about how it's changed, how the applicants changed versus the years. Now, one thing I want to point out with years, as long as you're consistent, 2015 minus 2007 is the same as 15 minus 7. So it's okay to take a shortcut like that. We end up with 177.25, which would be approximately 177 applicants per year. So don't let the word problem throw you. You can still find the information that you need. Just be organized about it. What if we are given a function and they want us to find the average rate of change over an interval? They literally are saying from -5 to 0 for the x's. So we know the x's that we're talking about because it's right here. But what we don't know are the y values. But we have a function. So think back to how we can figure out the y value. Remember, g of x is just another name for y. So if I know my x value and I know my y expression is -x squared minus 6x plus 11, I can figure out what that value would be. So when x is -5, I'm literally going to take out all the x's and evaluate. I'm going to put a -5 in everywhere I had an x. And use parentheses because that will help you get the correct sign. If you type this into your calculator, the calculator will tell you that equals 16. -5 squared, that's like -25. -6 and 5 makes 30. And 11. That's how we get to the 16. You could also do -5 stored as x and then type this expression in your graphing calculator. It'll give you 16. Let's do the same for 0. -0 squared minus 6 times 0 plus 11. Putting those zeros in, we end up with 11. So now I want to think about how the y's changed compared to how the x's changed. And it doesn't matter which one I start with as long as I'm consistent. I went in this direction, so my x's have to go from left to right as well. When I do this, I get 5 over negative 5, which is the same as negative 1. Let's take a look at what that means graphically. So let's hop over to Desmos real quick and look at this graph. I look at the graph. It's literally asking from negative 5, which would be right about here, to 0, which would be here. So I want you to imagine taking a point here to here. What kind of line would that be? It would be right like this. Do you see that line that I just drew? What's the slope of that line? We're going down one, right one. Think back to Algebra 1. Negative 1. That means that if I were to average the slope, see how it's going up here and then it goes down? It would end up averaging out to be negative 1. That's literally what we're talking about in this example, but I wanted you to see it graphically as well. Speaking of graphically, this next example gives us a graph. And they want to talk about from negative 4. So when x is negative 4, we have this point. That looks like the point negative 4, negative 5. And the other end is negative 2. Negative 2, now we're talking about this point. That's the point negative 2, 5. So we want to know what would be the average rate of change from those 2 points. So again, I'm going to start with my y values. 5, take away negative 5. So I'm just going to make that a plus. Subtracting a negative is the same as adding. And then negative 2, subtract a negative 4, gives me 10 over 2, which is 5. That would be my average rate of change of this function on this interval. What if they give you a graph that has a lot of different intervals, going from here to here, here to here, and so on? Which one has the greatest rate of change? Well, we're going to have a little bit of work to do here. We're going to have to find 4 rates of change, but you start to get pretty good at it after a while. From this point to this point, all we have to do is 484, take away 64, 27, take away 10, which would give me 420 over 17, 24.71. This next one right here, now we're going from this point to this point to figure out the slope of this segment. So 898, take away 484, 30, take away 27, simplifies to 414 over 3, which reduces to 138. Go ahead and find the slope for this segment here and this segment right here, and then we'll compare them. So now we just need to compare these rates of change. On the first interval, it's 24.71 compared to 138, compared to 18, compared to 7.8. Which one is the greatest? 138. You can also think about it. I'm going to make a little stick figure here. Grab this stick figure. Think about this stick figure climbing up this hill. When would it be the hardest to climb? So we start off, it's a pretty steep hike. Once we get here, we're practically rock climbing straight up the wall. And then it gets a little bit easier. And then it gets even less steep. So we could have probably just looked at the picture to be able to tell which interval would have the steepest slope or the greatest rate of change. Now I've kind of been throwing out the word slope a little bit from Algebra 1 and from geometry because again, slope and rate of change are the same thing. The slope of a line is its rate of change. It's the same thing. This is the classic slope formula right here. Often slope is remembered as rise over run. Hopefully a lot of this is coming back to you from Algebra 1. Let's practice when we are given 2 points finding the slope. Now, again, the slope formula is right here. It's a good formula, but it has a lot of subscripts, which makes it look very complicated. I prefer to just think of rise over run. And when I do slope, this is all I write to start with. M equals a big line with subtraction on the top and the bottom. That's all I put. I don't put y2, I don't put x1. That's all I write. Then I look at my points. I make the y's look like eyes. Do you see how they look like the eyes? I circle them. And you might say, well, Mrs. Mark, why do you have to circle them? Doesn't matter. Well, it really does help you when you're trying to put the correct numbers in the correct places. If you just circle the y's, make the y's look like eyes. 3, 5, minus 4, 2. And I just drop them right into that formula. I just drop them straight down. Now, if we actually use the formula and the subscripts, we probably, that's y1, x2, y2, we would probably do 5 minus 3 over 2 minus negative 4, but we'll get the same answer. And to me, it doesn't make sense to have to crisscross these numbers. It gets confusing. So I prefer to just drop them straight down into the formula. And when we do this, we'll simplify to negative 2 over negative 6, which reduces to 1/3. Pause the video and try this next one right here. 1, negative 3, and 3, 5. Did you get 4? Hopefully you did. Let's try the last one. Again, here's my formula. Subtract over subtract. I'm going to make my y's look like eyes. 11. When I put that negative 9 in, it cancels the existing negative in the formula and becomes a plus 9. Negative 8 and 24 drop in on the bottom, and we're left with 20 over negative 32, which reduces to negative 5/8. The most common mistake is that people put the x's on the top and the y's on the bottom. Don't do that. Take a moment to circle those y's, put them on top, and then put the x's on the bottom. We can do the same when we have a line on a graph. We just need to pick some nice points that are on the line. So I look here and see this point and this point. This point would be negative 2, 0, and this point would be 0, negative 3. Using our slope, we would make the y's look like eyes. 0, negative 3. Cancels out that existing negative. Negative 2, 0. When I simplify, I get 3 over negative 2, which is the same as negative 3/2. Try these next two yourself. I think on the first graph, it's really tricky to find some decent points, so hopefully you found a couple. The second graph is a little bit easier, and there's our slope. What if we just have an equation? So now we have to think back hard to Algebra 1 and think about where the slope could be found when just looking at an equation. Well, we learned slope-intercept form, which is y equals mx plus b. And we know that the slope was the coefficient of the x term. So in this first example, the slope is just 3. In the next example, the coefficient of the x term is just 2/5. That's the slope. In the third example, don't let yourself fall into the trap thinking that it's the number right after the equal sign. It's the coefficient of the x term, which is negative 1/3. Then it gets a little more interesting because now I am not in slope-intercept form. I can't just look at this and see the slope, but it's there. We just have to rearrange our terms so that we get it in the slope-intercept form first. So now I have 3y equals 15 plus 6x, dividing by 3, and simplifying, I see that in slope-intercept form, I could easily see that the slope is 2. This is point-slope form. So if you recognize that, you could easily see that in point-slope form, this is the slope. But if you weren't sure, you could distribute and move that 5 to the other side. So we'd get negative 3/8 x. Multiplying here, we'd get negative 6/8, which is like negative 4ths. And then we'd add 5. In other words, we could add 20/4. So y equals negative 3/8 x plus 17/4. And that's still my slope. How about this one? There is no x term. There is no x. The slope is 0. You might want to put a note. The slope of any line that is y equals some number is 0. These are horizontal lines. If we were to graph this line, it would be straight across left and right at y equals 4. The slope is 0. There is 0 slope. How about this one? That's right, it's invisible. It's still the coefficient of x, so the slope is 1. How about this one? X equals negative 14. This would be undefined. Anytime you have x equals a number, it's a vertical line. This is a line that runs straight up and down vertically, and it's going to be undefined. Here's another one where we just have to get it into the correct form. So we end up with y equals negative 28 plus 7x. The slope would be 7. How about this one? Well, the coefficient of the x term is right here, but that is not the slope because this is not even a line. This is a quadratic, means this is a graph that is a parabola. We cannot just say the slope of that line because it's not even a line, which brings us to our last concept of this step, which is about whether or not something is a linear function. A function is going to be linear if there is no variable raised to a power other than 1. We can write all linear functions in the form y equals mx plus b, or f of x equals mx plus b. M and b are going to be real numbers. Let's look at some examples. These are all examples of linear functions or linear equations. These are not. You may not divide by a variable. That breaks the rule. You cannot have a variable in the denominator. Oh, cannot spell today. Variable. There we go. You cannot have a variable raised to a power of 2. You cannot have variables multiplied. So let's take a look. Are these linear functions? Yes. This is a linear function because everything's raised to the first power, nothing's in the denominator, none of the variables are multiplied together. What about this one? No. X is in the denominator. How about this one? No. We cannot have variables multiplied. All right, how about this one? No. X cannot be in the denominator. In this last example, yes, it satisfies all of our requirements. This would be y equals mx plus b, where b is 1/3, m is -3/2. Those are real numbers. This next example, is this linear? Well, can I fit all these points on the same line? No. When I try to put a line through these points, it fails. Well, you might say, well, pick some other points. Well, if I put a line through these points, I can't capture all the points in the same line because this has a bend to it. So this is not linear. Looking at a table of values, is this linear? Well, let's look at the rate of change or the slope between all the points. If the slope never changes, it's going to be linear. From here to here, we have a change of 25. From here to here, we have a change of 25. Here to here, a change of 25, and from this point to this point, another change of 25. How are the x's changing? Well, they go down 1, down 1, down 1, down 1. No matter which points I pick, I'm going to get the same rate of change, the same slope. 25 over 1, 25 over 1, 25 over 1, 25 over 1. So yes, this is linear.